Hi everyone. Just waiting for this to load. And then we can go. Amazing. That's muted. Hello. How's everyone doing? It is Wednesday. I hope you all enjoyed the eclipse if you were able to see it. I was in 100% totality, which is incredible. Today, we are going to be going over Unit 2 of AP Chem. So we have, what are we doing? We're doing Lewis dot structures, a bunch of compound things, ionic versus covalent. We're doing, I am back. We're doing VSEPR Theory, hybridization, all sorts of things today. The first about half hour, I have actual notes and guides and everything that we're going to kind of walk through. So I'll do like a 30-minute lecture or class, and then we'll start going through the packet. Now, this packet is available on my link tree. Yes, we're going to go over Stoic. That is, oh gosh. What unit is that? That would be Unit 4, I believe. So that's not next time, but the time after, I believe. This packet is available on my link tree. It has a bunch, and I mean a bunch of practice problems, as you can see by my key, of Lewis dot structures, all sorts of things like that. Today, because I'm going to go over a lesson style for the first half hour, we're going to go through all of the even problems on this. Where can I find the link tree? It's the link in my bio. I just don't like saying link in bio for some reason. But if you just click on my profile, it'll pop up the link right there. It'll bring you to my link tree, and it's just where I have all of my links. So yes. I have my coffee. We'll wait just a couple more minutes until we get started. How is everyone doing with this unit? So this is VSEPR Theory, geometries, molecular orbitals, Lewis dot structures. Will this video be posted on YouTube? Yes. So all of my lives that I do are going to be going on YouTube. So typically, it will be posted the night of. So the live, depending on how fast it will download and the length and stuff, and upload to YouTube. When will you be going over redox? So that's going to be the last one I do, because that's Unit 9. So that'll be the end of the month, I think. If I can, I'll try and get to it sooner. I will post a couple videos specifically going over some redox problems, like balancing redox reactions, and that sort of stuff. Because they're really not that bad if you just get the formula. You're struggling with these, well, hopefully we'll be able to talk about some stuff. I just started Chem, and your sig figs video saved me. Thank you. I'm glad. That's one of my first videos that I did on these sort of helpful information, and I actually rewatched it recently. I'm like, wow, my editing skills back then were not good. I've learned so much about editing in the, I want to say 6 months that I've been doing these types of videos. It's always just weird because you have to start somewhere. You're going to not enjoy some of the stuff that you do. Okay. So let's see here. Oh, I love all the hearts and everything. So we'll give it one more minute, then we'll start. Again, periodic trends. I don't think I have a dedicated video specifically to periodic trends. I talk about periodic trends in certain videos, like I'll talk about electronegativity or atomic radius when we're talking about bonding and stuff, but I don't think I have a dedicated video. I can add that to the list, though. I will add that to the list. Before we start, this packet of questions, they are AP-styled questions. I take all of these from various AP resources, but it's definitely good practice even if you're not in AP Chem. This unit is on compound structure and properties. I'm sure you did, Trista. I'm sure you did amazing. And then even if you didn't, that's okay, because you'll learn from your mistakes. Sometimes you need to fail a little bit to succeed. I've learned that the hard way. But if you want this PDF of these problems, it is on my link tree. Just click the link in the bio. I hate saying that, but click the link in my bio, and it's under helpful information. It's like review session materials. You'll click that. It'll take you to Google Drive. I have all of the units that we've gone over, all of the PDFs up there, as well as the answer key. This particular one, the PDF is up there, but the answer key is not up there yet because we're going to go over it. So as a quick reminder, this session we will talk about VSEPR theory, hybridization, Lewis dot structures. We'll talk about different types of bonding. It's going to look a little different in this review session. There's a lot of concepts, and so I'm going to discuss them. I'm going to hold like a class for a little bit, like a 30-minute class, going over notes, some topics, and then we'll jump into the practice problems. Because I'm doing the half-hour thing, we're only going to go over the evens on here, but all of the answers along with, and as you can see, I do make a lot of notes on the answer key as to why things are the way they are. All of that will be up later today. So what I'm going to do is I'm going to get set up. Give me just a moment here so I can switch from this to this. I am not a school teacher. I am a graduate student in my final year of my PhD in chemistry, and I have tutored and taught chemistry to hundreds and hundreds of students. And so, yeah, I just love making chemistry easier for people. So give me just a moment. I'm going to switch over to my setup. And this is always the fun part where you get to see my ceiling. Beautiful. We'll flip camera. We'll do a little twisteroo. And we'll do something like this. It seems like it's backlit today. We're going to turn that just a little bit so I have this. Let me go turn off my other light real quick. Oh, maybe it's because it's still light out. All right. So it looks like we can see this. What is going on? Let me turn this one off and see if this... Nope, it's because it's still light out. That's what happens when things happen, or when it gets summertime. So you're going to see my little setup and probably my fingers in the screen as we go through this until it gets darker out. So what we're going to talk about today is compound structure and properties. We're going to go through the different types of bondings. We'll go through Lewis dot structures. We'll talk about energies associated with these. We will also talk about VSEPR theory and hybridization. So this first half hour is going to be a lot of me talking, and then we'll jump into the practice problems. So let's go through and start talking about these. I'm just going to raise this up a bit so I have a little bit more room underneath here. So when we talk about compounds, we're talking about things more than one thing. We have three main types of compounds. We have metallic, covalent, and ionic. So those are the three main types. Now, with something that's metallic, that'll be primarily, whoa, I cannot see. I'm going to have to turn my brightness up just a little bit because I can't see my screen at all. So when we talk about metallic, we're talking strictly about things that are only metals. So we only have metals in our compound. So something that's metallic, it could be a block of iron, a block of zinc, for instance, or some combination of different metals. Now, this is a really interesting bond because electrons inside this metallic bond are shared equally. So if we had like a block of iron, so let's say this whole entire brick right here is iron. Well, We have iron and iron all throughout, because it's just iron. But then we also have electrons, and these electrons are scattered throughout our block of iron. Now, these electrons are shared equally by our iron atoms, so our nucleus with our protons and neutrons. So our iron atoms are here, but our electrons are sort of spread all out. Now, they're not localized, and that word delocalized just means that your electrons are not specific to one atom. They're not bound to, like, if this was one iron atom and then that was its electron. It's just saying that we're delocalized. We're not in this sort of bound scenario. So let me get rid of those. And so metallic is just metallic or metals together. Primarily, you'll see metallic when it comes to metal solids like alloys and stuff. So we'll talk about substitutional and interstitial alloys in a little bit. Exactly, like lattices and everything. And then, so that's all metallic. Let's talk about covalent. Covalent is probably one of the more prominent ones that we'll talk about, especially today. Covalent is a bond between a metal and a non-metal. So if we were to look on a periodic table, and I don't have one here right now, we'll talk about one later, but we have that staircase, the big bold line down the right-hand side of the periodic table. Everything to the left of that is going to be a metal, and everything to the right of it is going to be a non-metal. So if we have two things, one of a metal and one of a non-metal, one to the left of the staircase, one to the right of the staircase, we're going to have a covalent bond. And a covalent bond, sorry, that's not a metal and a non-metal. Y'all need to correct me on this. What is going on? It is Wednesday. No one's listening to me. There we go. That's ionic. Thank you. Yes, it is between two or more non-metals. This is what happens when you teach for 12 hours today, and then you come onto a live. So covalent is between two or more non-metals. So we're going to do non-metal plus non-metal. There we go. So this happens. So non-metal and non-metal. So if we were to look at the staircase, right? So we look on the staircase. Everything to the right of that staircase on the periodic table is a non-metal. So if we had two or more non-metals together, then that would be a covalent bond. Now, some teachers, some classes have you go a little bit further, and they tell you to look at a pure covalent bond versus a polar covalent bond. Now, a pure covalent bond is when you have something where the electrons are shared equally. So let's take a look, for instance, at H2. So if we have hydrogen, this is H2, this hydrogen is bound to another hydrogen. And so inside this bond, right, inside a bond, we have two electrons. Now, if we were to look, each hydrogen is pulling on one of those electrons equally. So our electrons are sort of shared equally between each of these hydrogens. Versus our, let's say we have hydrogen and chlorine, so an HCl bond. Both of those are nonmetals. We have a hydrogen bound to a chlorine. And we'll go over how to draw all of these structures in a moment, or later on. But our hydrogen doesn't pull on our electrons in this bond the same way that the chlorine does. And this is all due to electronegativity. So electronegativity is the pull for electrons, and we'll show that in just a moment. But chlorine has a higher electronegativity. It wants those electrons. So instead of those electrons sort of favoring equally here, being shared equally, they're a little bit closer to that chlorine. And that allows for a partial negative charge to be put on that chlorine. And then because we have a negative charge here, a partial positive charge will be on that hydrogen. And so a pure covalent just means we're non-polar, we're equally sharing our electrons. And then if we're talking about a polar covalent bond, we have an unequal sharing. One of those atoms in a bond is pulling the electrons closer to itself, creating this partial negative charge and a partial positive charge. And we can see that here in these diagrams. We have an equal share sort of between these two. We see this gold sort of electron density being shared equally versus our electron density is higher on one of our atoms than our other, creating a partial negative charge here. So we have polar covalent and pure covalent. And then we also have what we were talking about earlier, as I mistakenly put it, we have ionic. And this is between a metal and a non-metal. So if we have something from the right of the staircase and the left of the staircase together, we have our metal and our non-metal. And ionic bonds are really interesting because we don't have any sharing of electrons, right? In a metallic bond, we had electrons being shared, but they weren't localized. They were just sort of scattering around all over the place. Covalent, they're localized, they're being pulled a little bit closer, but we're still sharing those electrons. Ionic, it's a complete transfer of electrons. If we have a metal and a non-metal, let's say we're talking about, I'm going to use sodium chloride, NaCl. Sodium is a metal, chlorine is a non-metal. Now, sodium, metals love to lose electrons and nonmetals love to gain electrons. So if we were to look, and we'll go over what all of this means in a moment, but sodium has one valence electron, or one electron in its outermost shell. Chlorine has 7 valence electrons, or 7 electrons in its outermost shell. Now, metals, they will lose their electrons and nonmetals will gain. So when we're talking about an ionic bond, our metal, this electron right here, is going to be transferred, not with a straight line, but with an arrow, transferred from our metal to our nonmetal. So now we end up getting a full positive charge on our metal and a full negative charge on our nonmetal, which is different than up here, right? We do have a negative and a positive, but they're partial. So these partials just tell us that we're creating a dipole moment, or just a little negative charge and a little positive charge. These are full negative and full positive charges. Let's see. So in a metallic bond, are different metals ever bonded together, or are they merely physical changes? So they actually can be bonded together, and those are called alloys. So if you have, let's say, I don't even know, like if we had, here, I'll just show you this right here, because we'll go over this in a moment, but so something like this, where we have two different metals, or two different, that's not a good example. We'll just look at this for a moment. We can have some substitution in here where we have a metal sort of coming in, replacing a different metal, or we can have other things in here. So it doesn't necessarily have to be strictly a physical change. You can have different metals bound together. More often than not, though, your metallic bonds are going to be a brick of one metal. The only reason we would have something different is if we have an alloy to do some type of, to make it sturdier or something along those lines. Like steel, for instance. Steel is a mixture of two different metals, I believe. Brass is copper and zinc, I believe. So there's a couple of them. So this is a brief overview of what our different bonds are going to be. We have metallic, covalent, and ionic. Let's see what's next, because I honestly forgot. This famous graph here. So we can tell, so this graph you'll probably look at and like, what is this graph? Well, let's break it down. This graph is plotting on the y-axis potential energy and on the x-axis internuclear distance. So let's say we have two atoms, and we're just sort of transferring them close to one another, and then we can kind of go further away. So we're sort of saying, are they really, really close? The distance between their nuclei, so the different distance between their centers, are they very close or are they further away? And we can measure the energy associated with that. And that's this potential energy. So we have a potential energy and the distance between the centers of the nucleus. And in almost every case, we have this trend where we start up very, very high and we go down and then go back up and sort of plateau out. This is AP Chem, yes. So we go down and back up. At number 1, we are at this point where we have very, very, very close internuclear distance, right? Where at this point here, our internuclear distance is very, very close and our potential energy is way, way up there. We don't want it up there. A bond likes to sit when it's at its minimal amount of energy. And so as we start to break those, separate those ions a little bit more, we're sort of taking the distance between them is increasing because we're going on our x-axis, our distance is increasing. We get to a minimum, and this minimum is our number 2. And that number 2 tells us our bond distance. So this is our bond distance, where we have a bond from the center to center. And so we can mark this X here as our bond distance, our bond length. And if we were to just make a mark all the way up to the top here and look at the x-axis, sometimes it's up to 0, sometimes the x-axis is down here, but that is going to be this distance here is our bond length. We want our bond length to be the minimum of this sort of potential energy. And then as we start to separate them even further, our potential energy goes back up until we are no longer existent. So this is where they get very, very far apart and they're no longer forming a bond. And these graphs are very, very good for us to view so we can look at our bond lengths, but then we also gain other information. And that other information, if we look on the y-axis, and we were to match up that bottom point here, the minimum point, we see that it's hitting this potential energy. And this is the energy needed to break a bond or form a bond. So, right, if we're breaking a bond, we have to put in energy. When we're forming a bond, we're releasing that energy. And so we get a lot of information out of this graph. We see that we can start up very high when they're very close. And as we separate them, we get to a minimum where our atoms, our compound, our bond is very, very happy. And then as we start to pull them apart again, even further, they are going to just forget about each other, right? Our potential energy is going to go to 0. They won't form a bond. Now, all of this is related to this here, Coulomb's law, where our force or our energy, that F, is proportional to, that's what this little finicky sign is proportional to the charges multiplied together of each of our atoms divided by the radius squared. So if we want to have a really high force, then we can kind of figure out what we need. We want very large charges on the atoms, and we want a short distance. So the shorter the distance, the higher the charge, the more potential energy we have, which is our minimum on this graph. So this is a very brief overview, and we'll go over a couple examples in a bit. But as we start to see, we can sort of play around with this. Sometimes graphs, they'll have bonds going over like this. And we can say, well, we have a lower potential energy, we have a longer distance, and we can pull a lot of information out of them. Amazing. So now let's talk about electronegativity. Is energy needed to break the same as activation energy? The energy needed to break a bond can be associated with activation energy. If that's all that you're doing, if that's all that you're putting into, like that's the only reaction, then yes. But most of the time, there's other things going on. You're breaking bonds to form other bonds. And so it's most of the time you're breaking more than one bond. So it's like the combination of all of those energies is the activation energy. And it's the energy needed to allow the overall reaction to occur rather than just breaking one bond. Unless, like I said, your reaction is only to break that one bond. So let's talk about electronegativity for a moment. Now, electronegativity, we sort of touched upon a little bit. That is the pull for electrons. That's the want for an atom to really pull, or its attractedness to electrons. So the general trend on the periodic table, this is where we're getting into a little bit of the trends, is that as we go across from left to right on a row or a period on the periodic table, our electronegativity increases. And as we go from bottom to top, our electronegativity will also increase. So if we were to sort of put the two of these together, if we go from the bottom right to the top left, that's going to be the general trend. Our electronegativity will increase as we go from bottom right to top left. Fluorine, that is the most electronegative atom, or element, right? So it has an electronegativity of 4. Now, if you notice here, all of the noble gases, they do not have an electronegativity. And that's because they are happy just the way they are. They have already fulfilled their octet or doublet, or they have the right amount of electrons to be happy. They don't want to gain anymore. They don't want to lose anymore. And so they don't have an electronegativity assigned to them. And so we can use these values here. Someone decided to give each one of these atoms, I don't know how they did it, but they decided to give each one of these values to an element. Now, the higher the number, so it's on a scale from 0 to 4, the higher the number, the more electronegative something is. So fluorine, being the most electronegative, was given the value 4. Now, all the way down here, we have the least amount, which is 0.7. Now, depending on what we're looking at, we can compare electronegativities, like carbon versus fluorine. Carbon is 2.5. It's hard to see from this angle. 2.5. Fluorine is 4.0, and that follows the general trend. As we go across a period from left to right, then we are getting into more electronegative elements. Yes, that means fluorine will pull on the electrons the most. So anytime you have something with a fluorine, that fluorine is just going to be grabbing those electrons, pulling them closer into a tighter hug. Exactly. So we can actually figure out the difference in electronegativities. And we can use that sort of difference to help us figure out if something is polar or non-polar. Polar just means we have a difference in our electronegativities, right? A polar bond would mean that we have some difference in electronegativity, some difference in pull of our electrons, versus something that's nonpolar is equally shared. We have a net 0 or very close to 0. So going through this, if we were to look at the electronegativity of H2, an H2 bond, well, we would see that one hydrogen is 2.1, and the other, because we have another hydrogen, that is also 2.1. So the net overall electronegativity, or the net dipole here, is 0. So this would be a nonpolar bond. But as soon as we get into something like HF, where we have 2.1 for hydrogen and 4.0 for fluorine, well, then we take the difference. 4.0 minus 2.1, that gives us an overall net of 1.9. And this is going to be a polar molecule. And then we can write our dipole moment in. We can actually show which way the electrons are being pulled. And we use an arrow for that. I'm going to choose a different color here. We are going to draw an arrow, and the arrowhead, that point, is going to be towards the area of the molecule or the bond where we have our more negative piece. And then we always put this little dash at the end where we have a positive. And I like that dash because it reminds me of a plus sign. So that plus sign or that dash should go to the more positive end of your bond. And then we go, and our arrow is pointing in the direction of where our electrons are being pulled. And so overall, we can say, because we have this dipole moment here, on the fluorine, we have a partial negative charge because electrons are being favored and pulled in this direction, where we have a partial positive charge on that hydrogen. And then we can do the same thing for carbon and chlorine. Carbon, we said, was 2.5. Chlorine is, if we go here, that's 3.0. So 3.0. We can do the subtraction. We end up getting a net of 0.5 in the direction of chlorine because that's higher. Again, we'll do our net here with our positive on the carbon, our negative on the chlorine, so that arrowhead points towards our chlorine. And this is an overall polar bond. We can use this notion also to tell what bonds are going to be more polar than others. So, for instance, an HF bond is more polar because we have a higher difference in electronegativities between hydrogen and fluorine. It's more polar than a carbon-chlorine bond, where our difference in electronegativity is 0.5 versus 1.9. Polar means there's a value difference. Nonpolar means there's no value difference. Exactly. Most of the time, nonpolar means there's no value difference. If there's a value difference of like 0.1, it's going to be slightly polar, but it's going to lean towards nonpolar. But for your purposes, absolutely yes. So if there's a difference in our electronegativities, we're going to have an unequal share of our electrons. What about a CH bond? That's a good question. So if we were to do a CH bond here, let me kind of write it. I hope you'll be able to see on the bottom here. If we do a CH bond, well, our carbon is, if we look here, our carbon we said was 2.5. Hydrogen is 2.1. So there is going to be a difference in our electronegativity, right? We have 2.5 and 2.1. So our difference here is 0.4. So this is going to be a polar bond. It's very, very tiny, but there is a little bit of polarity here. And it's going to favor our carbon. So if we draw a little arrow here, it's going to favor, so our electrons are being pulled slightly closer to our carbon. And then we have our positive sign there. So these are just bonds. So this is not getting into our overall molecules. Yeah, these are just the bonds themselves. And yes, generally speaking, if it's not a large difference, then you can say that it's nonpolar. But if C and H are bonded to each other, therefore they are nonpolar. That is not entirely true. Are polar and nonpolar typically stronger in terms of IMF? Let me think on that. Yes and no. So IMFs are between different molecules, whereas our bonds or within one compound, that is a little bit different. But yes, you can think of it IMFs as typically stronger for polar and nonpolar. All right. So that is a electronegativity in a nutshell. Polar molecules have dipole-dipole, but non-molar, non-polar one only. Oh my goodness, it's late. Polar molecules have dipole-dipole, but non-polar only have LDF. Yes, that is true. And our next couple review sessions are going to be on IMFs and solutions. So we'll go over all of those for intermolecular forces and everything. We'll go over all of those, I think Saturday and next Tuesday. So we have a couple of sessions strictly on those. All right. Am I going to do nuclear? Nuclear chem, yes. I believe it is the final unit. So it's going to be towards the end of the month now. End of the month of April. All right, so this is electronegativity. Now, we use a lot of these electronegativities and we use a lot of this stuff to help us with drawing out our structures. Now, I don't know how you were taught, but I'm going to teach you how I teach my students to do Lewis dot structures. So Lewis dot structures. Lewis dot structures are simply ways for us to look at bonds. They're ways for us to take a look at a compound and figure out what atoms are being bound to what other atoms. Do we have any lone pairs or not unpaired or non-paired electrons? Do we have double or triple bonds? Like, what is going on in the overall molecule? And so we use a lot of these different things to help us with reactions, to help us with bonding and bond order, lone pairs, orbitals. There's a bunch of different things that we use Lewis dot structures for. Lewis dot structures are two-dimensional. So these are strictly two-dimensional things. We'll get into our three-dimensional, our molecular and electron geometries in a little bit. But these are our overall just two-dimensional structures. Now, here's how I go about drawing Lewis structures. The first thing we want to do whenever we're given a scenario, we want to count up our number of valence electrons. Now, how do we find our valence electrons? Well, we look at the periodic table. If something is, so a valence electron is an electron in the outermost shell of an atom. And typically, you can use the trend. If it's in the first column, it has one valence electron. Then the second column will be 2. Then we can just skip the transition metals. No one really cares about them right now. So we skip all of those transition metals and we start again over on the third column. And we are going to go 3, 4, 5, 6, 7, 8. So it goes 1, 2, skip, 3, 4, 5, 6, 7, 8. And so if something's in the fifth column, like nitrogen, it's going to have 5 valence electrons. Once we figure out the total number of valence electrons that we have coming into our compound, then we look and figure out what is going to be the center atom. Now, the center atom is going to be the least electronegative or most electropositive. So if we remember our trend that we were just talking about, electronegativity increases as we go from bottom left to top right of the periodic table. So if we want our molecule to have a center atom that is most electropositive, we're going to want it somewhere either down here, or when we're talking about covalent bonds, we're going to want it over in this area, sort of further down. Now, once we have our center atom, we will draw our center atom in, and then we are going to just write in our other atoms. So everything else is going to go around that center atom. And we'll connect each one of those with a bond. Now remember, each bond, each line that we draw contains 2 electrons. So this bond here between nitrogen and chlorine, that is 2 electrons. So anytime you see a line, you have to remember 2 electrons. By drawing in those bonds, and we'll go over an example, but by drawing in those bonds, we see we use some of our valence electrons. So we're going to figure out how many we have remaining, and then we go ahead and put in the rest of those. And we're going to start with our outer atoms and work our way in. So we want to make sure that all of our atoms will fit and obey the octet rule. And the octet rule just means that an atom likes to have 8 valence electrons around it. Let's take a look at this nitrogen here. Nitrogen, it's the center atom. It has 1, 2 lone electrons and then 3 bonds. Each one of those bonds has 2 electrons, so 2, 4, 6, 7, 8. This nitrogen has a full octet. Same with each of these chlorines, right? We have 1 bond with 2 electrons and 2, 4, 6 other lone electrons. So we have a total of 8 electrons. This carbon over here doesn't have any lone electrons on it, but it has 4 bonds, right? A double bond here and a double bond here. Each one of those bonds has 2 valence electrons, so we have 2, 4, 6, 8 around that carbon. Atoms love to fulfill the octet. There is 2, 3 exceptions, I'll say. The first is the doublet rule. Now, the doublet rule applies to hydrogen and helium, and that just states, well, hydrogen being where it is on the periodic table, it can't fulfill an octet. It only has an s orbital. It can only have 2 electrons around it. So the doublet rule tells us that hydrogen will only ever have 1 bond to it. And that is shown here, right? We have a hydrogen and a carbon bond, but even though we only have the 2 from that bond, those 2 electrons from that carbon-hydrogen bond around this hydrogen, we don't put any more valence electrons around it because it does not like it. It likes to follow the doublet rule and not the octet rule. So that's one exception. The next exception is that we can actually expand the octet. Sometimes atoms get very, very, very large, especially as you go down a group on a periodic table, and they can actually expand their octet. Now, the general trend is that anytime you get to phosphorus, so phosphorus and below, you can expand the octet. Now, it all depends on the number of valence electrons, the total number that you come up with. And we'll see some examples of the expanded octets. Not every atom can expand their octet. You have to have an atom that is large enough. So anything from phosphorus down, so phosphorus, xenon, bromine, iodine, anything past period 3 typically can expand the octet. It's not always going to expand the octet, but it can if needed. And then the third exception is sometimes, there's a very few, but sometimes it won't fill a doublet and it won't fill an octet and it won't expand the octet. And that's what we call, well, I don't even know if there is a name for it, but let's take BH3 for instance. Well, first step is to count the number of valence electrons. Well, we see we have, why isn't that going away? There we go. We have boron, which is right here. That is in 1, 2, 3, so it's in group 3, so it's going to bring 3 valence electrons, and each hydrogen is going to bring 1. So we have 1 coming from there, but we have 3 of them. And so we have 3 plus 3 giving us 6 valence electrons. So if we were to draw this, boron over here, when we looked at the electronegativity and everything, boron will be our center atom. We determined our center atom. We're going to draw in the outer atoms. So we have hydrogen, hydrogen, and hydrogen, and we're going to connect each one of those with a bond. Now, each one of those bonds has 2 valence electrons. So we have 2, 4, 6 valence electrons that we have already used. But if we look, we have no more to put in. And so our hydrogens are happy because they fulfill the octet, or not the octet, the doublet, right? 2 valence electrons around there. But boron has 2, 4, 6. It doesn't have a full octet. and that is okay. I like someone saying it's an incomplete Lewis structure, right? It's not going to have a full octet, and that is totally, totally okay. Generally, it's boron, aluminum, it's everything sort of in this third column might not fulfill a full octet, and that is totally, totally okay. Let's go through, I'm going to go through an example here. We'll go through one full example. So let's say we want to determine the, we want to determine the Lewis structure for, I'm going to do carbon tetrachloride. We're going to do CCl4. So CCl4, the first thing we do, we count up our total number of valence electrons. Well, carbon brings 1, 2, 3, 4. I can't count tonight. So carbon brings 4 valence electrons, and chlorine brings 1, 2, 3, 4, 5, 6, 7. Chlorine is in the 7th period, so it's going to bring 7 valence electrons. But we have 4 of them, so we have to multiply that by 4. Each of those chlorines is bringing 7 valence electrons. So our total valence electron count here is 32. So we have 32 valence electrons to work with. Now we're going to determine our center atom. When we look at our periodic table, we see carbon and we see chlorine. We want our center atom to be the most electropositive, and the most electropositive between these two is going to be carbon. So our carbon here is going to go in the center, and then we're going to, I'm actually going to do a different color here to make it a little bit easier to see. So we'll put carbon here, and then after we determined our center atom, we are going to draw in our outer atoms. So I have 4 chlorines. 4 chlorines go in, and we're going to connect each of those chlorines to the center with a bond. So we'll connect each one of these chlorines to our center atom with a bond. Now, how many valence electrons have we used so far? We've used 2, 4, 6, 8. So how many more do we have left to put in? We have 24 left. So we have 24 remaining valence electrons, and we're going to start from our outer atoms and work our way in. Now remember, each of our atoms, our chlorines, wants to fulfill the octet. It's not one of those exceptions right now. So we're going to start by filling in our chlorines. Each chlorine right now has 2 valence electrons. Until we start to fill that octet, we have 3 more lone pairs of electrons. So each of those chlorines is going to get 6 more valence electrons around it. 1, 2, 3, 4, 5, and 6. Now how many have we used? Well, we put in 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 more. So we don't have any more left. Now, the last step here is to turn lone pairs into double or triple bonds if needed. We won't always have to do this, but let's say, for instance, we had a center atom that didn't fulfill the octet. Our carbon here does fulfill the octet, 2, 4, 6, 8, but let's say it didn't. And it needed more, but we didn't have any more valence electrons to put into or draw into our system. That's when we take a lone pair from an outer and just move it to form a double bond. Exactly like phosphorus. So we're going to take an outer atom and just move it to form a double bond. In this case, we don't have to do that, but it's just good to know, and we'll get some practice in a little bit. So if we were to double check this, each of our chlorines has 8 valence electrons, 2 from the shared bond, and then 6 around it, each of 8. Our carbon has an octet, so we're good there. And then let's just count to make sure that we have a total number of 32 valence electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So this would be our complete Lewis dot structure for our carbon tetrachloride, which we have right here. Whew, that was a lot. Now, if we look at this though, let's take a look. Let's talk about polar and nonpolar while we have this. If we were to look at this, each one of these bonds, so each one of these carbon-chlorine bonds, actually let's go back here. We have carbon and chlorine, right, with our electronegativities. So we do have some polar component to that bond. So each one of these bonds is polar. And I'm going to draw that sort of off to the side, where we have our electronegativity facing our chlorine. So each one of these bonds has a dipole moment, right? The electrons in these shared bonds are going to be pulled closer to our chlorines. But we're pulling them equally. It's like a four-way tug of war, right? We have equal and opposite pull, top to bottom, right to left. So even though each one of these bonds has a polar component to it, each one of these bonds is polar, the overall polarity of our compound is net zero, right? If we had a four-way tug of war and each person is pulling equally amount and equal force, that center flag, that center mark is not going to move, meaning that this would be a non-polar compound. If there's a lone pair in the central atom, it can affect polarity. It absolutely can, yes. So if there is a lone pair of electrons on that center atom, that can definitely affect whether or not it's going to pull one way or the other. So that is definitely a good thing, yes. You're one step ahead of me. Look at this. We're going to go right into VSEPR theory. Oh no, it's doing the bouncy thing again. Hang on a sec. I need to kind of raise this up. It was doing the focusing in and outs. There we go. We have not talked about bond angles. We're about to. So, Lewis dot structures, like we said, all of this right here, these tell us two-dimensional structures. Absolutely tells us just everything about two-dimensional structures. But molecules exist in the real world, right? They exist in the real world where things are 3 dimensions, right? This pencil is 3 dimensions. My coffee is 3 dimensions. Like everything is 3-dimensional. And so that's where our VSEPR theory comes in, or valence shell electron pair repulsion theory. And this, all it really says is we're turning our 2D Lewis dot structures into 3 dimensions. And we're doing this by a repulsion of our electrons, right? Electrons have the same charge, they're negatively charged, and so they're going to want to repulse. They're forces of repulsion. Hi, Kayla. We do love VSEPR, yes. So we're taking something 2-dimensional, like so, and we're going to make it 3-dimensional. And so our drawings are going to look a little different, and we're going to start to visualize things in 3 dimensions. And each one of our bond angles now is going to be the minimum, or the minimum amount, the maximum repulsion allowed. That's what it is. So it's the maximum allowed angle of repulsion. So something like this, where we have CH4, this has 1, 2, 3, 4 things around it. Now, in reality, we're not just going to say, well, this angle is 90 degrees and this angle is 90, because we have another dimension. We have our Z dimension. And so this is where we're going to start looking at these types of representations, where we have our center atom, everything that's just a normal bond that you see, so like our top one and this diagonal one here, those are going to be sort of in the plane of your paper, or in the plane of the board, or in the plane of our of my iPad. So they're just sort of flat on the table right now. So this, not including these 2 hydrogens here, but this hydrogen, carbon, hydrogen, we can think of it as my hand's doing this, right? We have a hydrogen here, carbon, hydrogen. They're just flat on the tabletop. Where we start to see things in 3 dimensions is when we have these dashes and wedges. Do they still count as a bond? Yes, they do. So they still do count as a bond. So we have these lines here that is a single bond. So we have one line here that is a single bond. We have another line here that is a single bond. Now we have this dash here. Now dash you can think of as down. The dashes, that's what it is. So the dashes is still one bond. So we have a dash and it's going away from me. It's going down into the paper, into the thing. So if we have this dash here, we can think of it as away, whereas the wedge is going to be coming up at you. So really it's sort of this hydrogen here is going into the paper and this one is coming up it's going into the paper, into the table. This one's coming out at the screen. Now, the general trend is you're going to want to still put double bonds and triple bonds in the plane of the thing. So if we had, I can't think of one right now, carbon, if we had something like this, that's going to be planar. I don't want that. I'm just going to do this. So let's say we had Cl and then you wanted to do like a double dash like this for oxygen, something like this. This doesn't really tell us a lot. It's very messy. It's very blah. And so what we like to do is we just do a double bond like this. So we try to keep our double and triple bonds in the plane if possible. Ethene. Now you're testing my knowledge. Let me see. Ethene. I don't know if I can do ethene. I mean, I can. I just don't want to explain it because it gets a little complicated right now. We're sticking with easier ones right now. But thank you, Kayla. Okay, so this is where we sort of get into our 3 dimensions, right? We're starting to see 4 things, and we have 4 things. Now, each one of these, instead of saying 90 degrees like we would have thought over here, this is going to be 109.5 degrees. And this is going to be 109.5 degrees. So each one of these angles is now 109.5. So the black bond is a double bond. This black bond here is a single bond right now. So the wedge just means that something's coming up at you versus a dash means it's going away. And yes, because it's tetrahedral, and we'll get into names in a moment, we have a 109.5 degree difference. So this is valence shell electron pair repulsion, exactly. So let's talk about a little bit more. Because we're taking something in 2 dimensions and putting it into 3 dimensions, we start to see things a little bit differently. The angles change. Instead of saying, okay, well, now we're at 90 degrees here, 2-dimensional, then we can go into 3-dimensional, and it changes the bond angles and maximizes the electron repulsion. This is where it's gonna get a little scary, and I'm sorry. But don't worry, we'll go through this. So we have a couple different things. We have what's known as electron geometry, and we have what's known as molecular geometry. We're going to focus just on electron pair geometry right now, so not about molecular geometry. We're just going to look at electron pair geometry. So electron pair geometry tells us the shape of the molecule with everything around it, with atoms, with lone pairs. It takes everything into account. And so when we look at something that, let's say, has 4 things around it, like this carbon here, we have a carbon with 4 different things around it. Well, we look at the number of things. This number of things is 4. And something with 4 things around that center atom is tetrahedral. Remember, we're only looking at our electron geometry. Now, let's say, for instance, I didn't have another hydrogen here. And instead, I had a lone pair. Now, this is just me explaining things. Don't think that this is an actual thing. But let's say we had a lone pair here, and I'm going to do a little bunny ear. Now, a little bunny ear is a lone pair. Now, that's going to change our overall, it's not going to change our electron geometry, because our electron geometry takes everything into account, including atoms and lone pairs. So our electron pair geometry is still going to be tetrahedral because we have 1, 2, 3 atoms and 1 lone pair. So we have 4 things around it, and that is tetrahedral. Now, as soon as we put in that lone pair, it changes our molecular geometry, because molecular geometry, we're only looking at the other atoms, the shape of the molecule with the other atoms. And so when we're looking at now this shape, we're going to sort of ignore this lone pair here. Still keeping everything else the same, but we're going to ignore that lone pair. And if we ignore that lone pair, it's no longer tetrahedral. And now we're getting to something that looks a little pyramidal, right? Because we have a carbon and then it's sort of like propped up with 3 things, kind of like a tripod in a sense. So this becomes trigonal pyramidal. Pyramidal because it's going to be a pyramid. We have a point and then some things coming off of it. And then we have a trigonal because the base forms a triangle, right? 1, 2, 3. Now, if we had 2 lone pairs, that would change it. We would get rid of another one, and we'd have 2 lone pairs. Now we're bent. So our overall electron geometry includes everything. Molecular geometry only includes our atoms that the center atom is bound to. Now, this will also, and I saw some comments, this will also change the bond angles. So our bond angle for tetrahedral, like we were talking about before, that is 109.5. Let me zoom in a little bit. Got to verify to continue. There we go. So our tetrahedral is 109.5. But as soon as one of the lone pairs is put in place of an atom, it pushes our electrons, our other atoms, closer. And this is going to be, I just say, and I teach less than, well, that's, there we go. I'm still on white. Less than 109.5. Some people will have you memorize them as 104.5 or 107.5. I just say less than. That's what I typically teach, is if you are going from something with no lone pairs and you know the bond angle, just put a less than sign in front of it when you start adding electrons, lone pairs of electrons. So let's go through and just look at a couple of these. So if we have a center atom with 2 things around it, our electron geometry is linear, meaning it just forms a line, right? So if it forms a line, our bond angle, and I didn't put that in there, is 180 degrees. It's completely linear. So this whole area right here that forms is 180 degrees. If we have a center atom, we looked at one earlier of boron trihydride, which is BH3, we saw that it formed 3 things around it, and so it sort of forms a triangle. But the triangle is going to be trigonal planar, so everything is still in a plane, it's still in the same realm of the paper, and we see that it's going to be trigonal planar with 120 degrees, because if you were to cut a circle, which is 360, into 3 separate pieces, then you would have 120 degrees. But as soon as you take one of those away, now we have 1 lone pair. Now we're sort of bent, right? We have our center atom, 2 things around it, but it's bent. It's not in a straight linear line now. They're just bent. if anybody is taking the AP Chem, the readers require that students put a limit on less than. Okay. Thank you. Thank you for that. So then we see tetrahedral. So no lone pairs. Our electron geometry, something with 4 things around it, is going to be tetrahedral. Then as soon as we pull one off, we saw that up there, it becomes trigonal pyramidal or pyramidal. And then we pulled 2 things off, so we have 2 lone pairs of electrons. Now we are completely bent. Then we get into our expanded octets. And with our expanded octets, we have our trigonal bipyramidal. So something with 5 things around it is trigonal pyramidal. Or trigonal bipyramidal. And if we look, if I cover up this one right here, we form a triangle, 1, 2, 3, with a pyramid. But then if I uncover that one, we have a pyramid on the bottom too. So it forms a pyramid up top and a pyramid on the bottom. Angle for bent, that is less than 109.5 or less than 120. I think some of them, some of the readers require you to be specific. I have always just said less than. Typically, it's a range, like 104.5 to 109.5, somewhere around there. And then one of my favorites is the sawhorse or seesaw. And that is when you put in a lone pair. Now with trigonal bipyramidal, you take from the center first. So you're going to keep that top and bottom, you're going to keep those the same. You're not going to put in a lone pair there first. You're going to put your lone pairs right around that center ring. Now, if you put one on the center ring, and imagine, actually you don't have to imagine because I can tilt it like this. Now we have a seesaw. We have something coming at me right here. We have something going behind. If someone were to sit here and someone were to sit here, it would just go, and it's a seesaw. It's one of my favorites. Then if you take another one off from the center, so you have 2 lone pairs of electrons on the center, and you were to sort of tilt it around, you would have a T shape. So you would form a T, and you take that third one off, it becomes linear. So we have 3 lone pairs around the center, it becomes linear. And then the last is octahedral. It has 6 things around it. You might think it has 8, but it actually has 6 things around it. No lone pairs will be octahedral. If you take one lone pair, if you put one lone pair on, then you like flip it down. Now it becomes a square. It has a square base and a point on top, so it becomes a square pyramid or square pyramidal. Then if we, whoa, my brightness went up a lot. I don't know what happened. And now it's going back down. Then we take another one off and it becomes square planar. As we add another lone pair of electrons, we get that T shape again, and one more gives us linear. Yes. Actually, that is not 100% true. For the most part, if a compound has lone pairs, it is almost always polar, but that is not always the case. Okay. So let's go ahead. I know this table is a lot. I'm going to turn up my brightness a little bit because it seems like you could see. Is it this light that's like shining? Give me 1 sec, y'all. I'm just trying to make sure that you can see. There we go. That's much better. Okay. So I'm going to turn this up. Why does it keep doing auto brightness? I think I have auto brightness on. That's why. So something that helped me memorize this is this PhET simulation. And actually, if you go in my link tree, it's under the helpful information. I have a link to it. It's an online resource that is, you can visualize these things. You can put different bonds on. You can add lone pairs. It will help you with bond angles. It'll help you with molecular and electron geometries. You can quiz yourself on it. It is super duper helpful. So this PhET simulation, I forget where it comes out of, Colorado maybe, but they designed this whole online thing. And so it's absolutely amazing and helpful. Now, I saw someone in there, where do these sp3 hybridizations come into play? And that's what we're going to talk about next. We're going to go through these hybrid orbitals. So with hybrid orbitals, you've heard this term before chemistry. You've heard this term in cars, hybrid cars, a mixture of electric and gas. You've heard hybrid animals like a lion and tiger mix, hybrid. There's other ones that I can't think of right now. But you've definitely, hybrid learning online and online and in person. So there's a lot of different things with hybrid. So that just means a mix. Hybrid simply means a mix of orbitals. Or hybrid orbitals means a mix of orbitals. Now, I'm going to explain why these happen, and then I'll give you a shortcut as to memorizing them. So carbon, if we were to look at the electron configuration for carbon, it is 1s2, 2s2, 2p2. That is the electron configuration. We find that on the periodic table, or we use the periodic table to help us. Now, if we were to look at the molecular orbitals here, and I did this in increasing energy, we start out with our 1s, it has lower energy, then 2s, then 2p. We start filling in our electrons, start from the bottom, working our way up in higher energy. And when we get to this point here, molecular orbital diagrams tell us how many unpaired electrons we have in our system, and an unpaired electron tells us that we can form a bond. Now, carbon, its electron, with its electron configuration and molecular orbital diagram, it has 2 unpaired electrons, meaning theoretically, it can only form 2 bonds. But we've done examples throughout the night tonight of carbon forming 4 bonds. In fact, carbon loves to form 4 bonds. Methane, for instance, has 4 bonds, and it's something that we can actually test for. We know that carbon has 4 bonds, but how can it form 4 bonds if it only has 2 unpaired electrons? This is where we get into a mixture of those orbitals. We are going to take our s orbital, our 2s orbital, and some of our p orbitals, and kind of just mix them together. This new hybrid orbital is going to be higher in energy than the s orbital, and it's going to be lower in energy than the p orbitals. It'll be somewhere in between. We're mixing them together. Now, we're taking one of our s orbitals, one of these boxes, and we're going to pull together the 3 p boxes too. So now we have what was our s box, s orbital, and our p boxes. Now that we have this new hybrid orbital, we are going to put in those electrons, right? We have our 4 electrons here. We start here, and we always go all the way across first. Now with this new hybrid orbital, we have 1, 2, 3, 4 unpaired electrons. So by forming this hybrid orbital, this mixture of s and p orbitals, we are trying to get to a stable configuration, absolutely, and we have now allowed for 4 electrons to be there to make 4 bonds, because as we know, carbon loves to make 4 bonds. And when we do this, we don't want to say SPPPP. We don't want to say that. We want to sort of make it a little bit easier, and this is the type of orbital that we call sp3, because we have our 1s here and 1, 2, 3 p's. So S1, P3. And so when we kind of look at this, we can say, well, instead of having a 2s and a 2p orbital, we now have an sp3 hybridized orbital where we have 4 lone electrons that can form 4 individual bonds. And we can do the same thing for sp2 where we only need 2 of our orbitals. We can add more orbitals. We can say, well, sp, pp, and then because we don't have any more p's, we can actually take from our d orbitals too. So this can become sp3d, sp3d2. There's a lot of different things that it can be. Now, how can we do this? How can we simplify it? Well, we can simplify it just by looking at this. Remember when we were talking about our molecular geometries and electron geometries, and we're looking at how many things were around, how many atoms and lone pairs were around our center atom? Well, what we're going to do is figure out how many atoms and lone pairs or how many things are around our center atom, count those up. If it has 2, well, then we have 1s and 1p coming from it, so an sp hybridized. If we have 3 things around it, we have 1s and 2p's, so sp2. Now, if you notice here, we have always 1s. And that 1s is because we're only able to bring, an s orbital only has 1 box. So we will only have one of our s's. The maximum number of boxes or mini orbitals in our p is 3. So as soon as we get to sp3, when we have 4 things, we have to move on to the next letter. So we can't say sp4 because we don't have a 4th box to take from. So we're going to, when we go into something with 5 things around it, we'll have sp3d. We have, and then a good way to check is just to count them up, right? 1 and 1 gives us 2. 1 and 2 gives us 3. 1 and 3 gives us 4. 1, 3, and 1 gives us 5. And it just matches up to the number of lone pairs and atoms, the number of things. What's the formula for formal charge? That's a good question. So I'll write the formula here. I think this is the last little bits of notes for hybridization. This is the last little lesson. This went way longer than I thought it was going to be, but I'm hoping that it was useful information. And then what we'll do is we'll do some practice problems for the next like half hour or so. So let's talk about formal charge real quick. Each atom that we are talking about, so in a compound, that is going to equal, so formal charge equals your valence electrons, so the number, I'm actually going to write it a little bit over to the side so I have a little bit more room. Formal charge is going to equal your number of valence electrons, or the electrons that are brought from that atom. We're going to subtract from that the number of non-bonding electrons, so lone electrons or non-bonding electrons, minus the number of bonds around that atom. So if I had something like, let's see, Cl, something like this, and I wanted to know about the formal charge of this chlorine, well, with our chlorine brings 7 valence electrons, minus non-bonding or lone electrons. Those are your little dots that you put in your Lewis dot structure. So 1, 2, 3, 4, 5, 6, minus the number of bonds. We have 1 bond around that chlorine, giving us a formal charge of 0. Now we want our formal charge to be as minimal as possible. So we want it as close to 0 as possible. All right. So I hope that was very, very helpful. That was very long-winded, but we're going to jump right into some practice problems. Now, someone just asked, could I please go over how to figure out if a molecule is polar or non-polar? Absolutely. We did spend a little bit of time on that, but in fact, it is something to do with the first question. So here we have, so if you want these practice problems, they are available on my link tree under helpful information. Just click the link. You'll be given you'll be directed to, directed to a Google Drive, and that Google Drive has all of these practice problems for every unit that we're going over, as well as the answer key. And because I haven't said this in a bit, all of these lives are recorded and posted onto YouTube. The link is also on my link tree. So we will definitely go through, we're not going to go through all of these problems today. There are a lot of them, but we'll go through a handful for the next half hour or so. Let me answer a couple questions real quick. Can you please review solution concentration? That is unit 3, I believe, and that's going to be on Saturday and Tuesday. So I'm doing 2 lives dedicated to unit 3 because it is the most heavily tested unit on the AP test. So I want to make sure I go over everything. The information that I am doing for that, the packets that I'm looking at are like 146 pages versus like 60 for each one of these units. So it's a lot different. Okay, so let's go on to number 1. Number 1 says, which of the following scientific claims about the bond in the molecular compound HF is most likely to be true? So we're looking for which one is going to be true about HF. Now, what can we say about HF without even looking at these answers? Well, hydrogen we can consider it a nonmetal. It's sort of considered a nonmetal. So we have H as a nonmetal. Our F is also a nonmetal, so we have a covalent bond. We can draw the Lewis structure for this and sort of figure things out from there. Now, hydrogen brings 1 valence electron. Fluorine brings 7 valence electrons. So we can go ahead and total those up for 8 valence electrons. We see hydrogen here. We bind it to fluorine. There's not really a center atom when we just have 2 things because they're just shares. So we don't have to look for that center atom. And we can go ahead and plug in or fill in the rest of our electrons. Because we had 2 that were shared from the bond, we have 6 left. So we put those around the fluorine because the hydrogen obeys the doublet rule and not the octet rule. So that becomes 0 here. So we don't have any more to put in. So this is our Lewis dot structure for HF. Now, if we were to, I'm going to go back here for a moment. If we were to look at the electronegativities now, we sort of did it a little bit here. We have 2.1 for hydrogen and 4.0 for fluorine. Fluorine is the most electronegative atom. So if we were to look at the electronegativities, or that pull for electrons, the higher the number, the more electronegative an atom is. So here, because fluorine is more polar than our hydrogen, it's pulling those electrons closer to it. These electrons in this bond, didn't mean to do that. These electrons in this bond are not equally shared right here. They're favoring or being pulled closer to that fluorine because it's more electronegative. So because the fluorine is being pulled, or the electrons are being pulled here, we're creating this partial negative charge on the fluorine and a partial positive charge on the hydrogen. And so here, this is sort of the setup of what HF is looking for. So if we go through these answers, there's a partial negative charge on the hydrogen atom. Well, we just determined that it was a partial positive charge. So we can go ahead and cross that out. Electrons are shared equally between the hydrogen and fluorine atoms. They are not shared equally, right? Because that fluorine is pulling those electrons closer to it. So that one is also not correct. The bond is extremely weak. Well, we can't really determine anything based on that. And so we can't determine how weak something is just based on our electronegativities and stuff. So we can go ahead and cross that one out. And the only one left, the bond is highly polar. Well, we already said that we have a partial negative, partial positive. we have a difference in electronegativity of 1.9, which is very, very high, meaning it is polar. And all polar means is that we have an unequal distribution of electrons. We're favoring one over the other. Smaller radius equals more electronegative. Yes, so I saw a couple comments there. How can we tell about electronegativities? Like, what determines electronegativity? It depends on the size of the atom along with the amount of electrons around it, the shielding effect. There's a lot of things that go into it. And someone determined, and they put values to it. So most of the time, you are given a table like this. What are the ranges? Well, the ranges for polar versus non-polar. Let me see here. So something that's polar will always have, so it looks like for the AP units, let me see here. Pure non-polar covalent bonds, you'll have anything between 0.0 and 0.4. So something between those are going to be non-polar. Typically, I like to say anything with a difference is going to be polar because that is technically true. But for the AP test, anything in this little range here is going to be non-polar. And then you have your pure covalent, which is a difference between 0.4 and 2. And then you have your ionic, which is just completely different. Beautiful. Things are falling over here. Okay, so let's go on to... where do I find this on YouTube? This will be on my YouTube, which is linked to my link tree. I think my handle is just my name, same as my username here, Bradley.check or Bradley check, one of those, CECH. And yeah, so I have all of those links in my link tree as well. I'm learning a lot. Yay, I'm glad. This is the fun part of chemistry where I get to help people learn. So I think for time's sake, because I'm already at an hour and a half, oh my goodness, I do not have anything for physical chemistry. I haven't gotten to it. I just started this sort of content creation and helping people this year, and I'm focusing more on high school chem, AP chem, honors chem, and general chemistry 1 and 2. But I do know that there's a lot of creators out there who do focus on different types of chemistries. I did make a video or a post on TikTok. It's like one of the ones where you can scroll photos and stuff of different content creators in chemistry that you should follow. I have one specific for organic chemistry. How do I get to the link tree? If you go to my bio, so if you go to my page, you can, so if you just go to my profile, there's a link on my profile. You can click that and it'll just pop up with a bunch of links. And YouTube will be on there. The PhET simulation, the VSEPR Theory simulation, that is on there, and a bunch of other things. All right, so let's go on. Let's go on to number 3. Which of the following can be inferred from the diagram opposite that shows the dependence of potential energy on the internuclear distance between two atoms? So we talked about this at the very beginning, where we have this graph here. Up at the very top, our distance is very, very small, so we have two things sort of overlapping. And then as we sort of separate them, we're going to find this sweet spot. And that sweet spot tells us our bond length, and it tells us the energy needed to break the bond, a bunch of other things, and then we get to a point where we're so far away that it's non-existent. Yes, the D is correct for that one. So here we sort of have this graph, and what can we infer from this? Well, we sort of just said that at this point here where we're at our minimum, that is our bond length. So if I were to, because I wrote over it, if I were to look at the internuclear distance, that x-axis, right at that bond length, that happens to be right about between 50 and 100, which would be 75. So our bond length here between these two atoms is 75 picometers, which, if we look here, the atoms form a bond with a bond length of 75 picometers. The atoms form a bond with a bond length of 25. That would be this point here when they're very, very close and they don't like to be with one another. The net force between the atoms is attractive at 75 picometer. That is not true because net force just means the attractive and repulsion adding up. Why is the bond length at the lowest potential energy? It's just where they're happiest, where they're not really, they're not competing for attraction and repulsion. They're just sort of chilling there. I don't know why I'm doing this, but it's the sweet spot. Instead of overlapping all of our orbitals, it found a very sweet spot of where it likes to be, and then too far away, it just kind of breaks off and they don't care about each other. It's like a bad breakup. They just go their own separate ways. Okay, let's go on to I like number 4. So let's do number 4. Is number 2 supposed to be that? No, sorry. Let me go back to number 2 because there is some confusion. My notes, I have D for some reason, even though I'm looking at my notes and I'm like, that doesn't make sense to me. Okay, we're going to do this. We're going to do number 2 because I want to make sure that I'm getting everything correct. So number 2, of the following single bonds, which is the least polar? So this is where we're looking at a difference in electronegativities. So if I go through, I'm going to quickly do this. You were to look at the table and you were to find that nitrogen is 3.0. Then we have hydrogen at 2.1. So every time there's a hydrogen, I'll put 2.1. Fluorine is 4.0. So fluorine is 4.0, fluorine is 4.0. Oxygen is 3.5, and iodine is 2.5. So we have these things here. Now, if we do the difference between these, we see that the difference is 0.9. We have a difference of 1.9, difference of 0.5, difference of 1.5, and a difference of, that would have been 3.5 here. So a difference of 1.4. So we're looking for which one is the least polar, which is going to be the smallest difference, which is actually choice C here, because that is the smallest difference. For some reason, whoever caught that, thank you, because I'm going to have to change my notes. For some reason, I made a mistake earlier. I think that's what it was. I made the mistake because I had 3.0 here, so I circled that one, and then I changed it and didn't go back and change the answer. So thank you for that. Sometimes I make mistakes. I'm not afraid to admit it. Okay, so now, nice job, everyone. So let's go ahead, and now we can go on to number 4. The potential energy as a function of internuclear distance for 3 diatomic molecules, diatomic meaning there's 2 atoms, 2 of the same atom, so X2, Y2, and Z2, is shown in the graph opposite. So we have these graphs here. Based on the data in the graph, which of the following correctly identifies the diatomic molecules X2, Y2, and Z2? So we have here 3 separate atoms. We have H2, N2, and O2. Now, if I were to look at the bonding between these, we have H2, we have N2, and we have O2. The bonding between them tells us that we have a single bond, a triple bond, and a double bond. Now, when we do this, the trend is that the higher the bond number, the bond order, or the number of bonds, the higher the bond energy, or the lower the potential energy. So the higher the bond order has the highest quantity of potential energy. So quantity meaning we just negate or take the absolute value. So highest quantity of energy. So if we look here, we have x2, y2, z2. Our potential energy, if we were to line these up, looks something like this, where our largest potential energy is this y2. Now, we just said that something with a high energy has a higher bond order, typically. So a higher bond order, higher number of bonds tells us a higher energy. And so we would expect that this triple bond, this N2, that would have our larger potential energy dip. Then, once we figure that out, these two are very close. There is a difference here. It might be hard to see, but there is a difference. If you weren't able to see that difference and it looked to be the same, then we go to size of the atom. And size of the atom, well, hydrogen is smaller in size. So hydrogen is smaller in size than oxygen. And since hydrogen is smaller in size than oxygen, it's going to have a smaller internuclear distance. So it's going to be closer to the left of the graph. So that hydrogen is going to be our x2, which leaves oxygen as our z2. So we have x is hydrogen, y is nitrogen, oxygen is z, which is choice A here. Amazing. Let's skip to number 8. We're going to get into some Lewis dot structures and stuff in just a moment. Just a moment here. So number 8. Steel is an alloy containing iron atoms and carbon atoms. Which of the following diagrams best represents the particle level structure of steel? So now we're looking at different alloys. All right, we have alloys here. And there are two different types of alloys, or two main types of alloys. We have substitutional, and we have interstitial. Substitutional is when we have two or more atoms in an alloy, a mixture of our elements in similar size. So we have similar sized atoms. Whereas interstitial is atoms, added atoms are much smaller than your main metal. So when we have substitutional, we're looking at something with similar size. So if we said, now I'm not telling you that this is the answer or not, but this would be something that is substitutional, where we have our atoms sort of alternating. We can take some of our carbon atoms and just substitute them with iron atoms. Whereas something that's interstitial, we have something like this, where we have our larger atoms all sort of placed in, and then throughout that, sort of weaved throughout it, we have smaller atoms sort of holding everything together, or sort of bound together. So what we have to determine is, are carbon and iron similar in size? Is it going to form a substitutional? Or are they interstitial? Are they different in size, very different in size? And for that, we look at the periodic table and we notice the trend. As we go from the top left of the periodic table to the bottom, or top right to the bottom left, our radius, or our size, is going to increase. Now, when we look at a periodic table, carbon would be up here, iron is down here. So carbon is much smaller than iron. So this is going to be an interstitial alloy, meaning that we can cross off C and we can cross off D because we know that they're different sizes, right? They're not going to be substitutional as well. So here we're between A and B. Now we just said carbon is much smaller than iron, so the correct answer for this alloy is choice B. How's everyone doing? I hope everyone is having a fabulous Wednesday night. We're going to go on and do some... We're going to go on and do some VSEPR Theory, Lewis dot structures, all of those. Normally, I go through a lot more of these practice problems, but I did spend a good hour and 15 minutes, I want to say, just talking about them. So I want to make sure that we fit as many practice examples in as possible within the certain amount of time. I'm probably going to go live for another half hour or so. I know I said that about a half hour ago, but I will say we'll say half hour. So 9:15 Eastern is when I'm going to stop. All right. So let's go ahead and do number 10. Which of the following has a central atom with less than an octet of electrons? So what you could do when you start this problem is draw out all of the Lewis structures. And that is one approach that you can do, is figure out valence electrons, draw out the Lewis structures, and figure out which one doesn't have an octet. The other thing you can do is figure out just the number of valence electrons. And why is that? Well, let's take a look. If we were to figure out the total number of valence electrons, each hydrogen brings one valence electron. And then we look at the periodic table, we would see that oxygen brings 6 because it's in the 6th column. So 2 hydrogen, 1 oxygen gives us 8 valence electrons. Nitrogen brings 5. I'll write them here. So 1 and 6. This nitrogen brings 5 valence electrons. It's in the 5th column on the periodic table. I notice my phone battery is getting low, so I'm just going to plug this in before it cuts my live off. There we go. So, and each hydrogen brings 1. So 3 times 1 is 3, plus 5, that's 8 valence electrons. Boron with 3 hydrogens. Well, boron brings 3. Hydrogen brings 1 each, giving us a total of 6 valence electrons. Carbon is 4, and we have 4 hydrogens, giving us a total of 8 valence electrons. And silicon is 4, with 4 hydrogens, giving us, again, 8 valence electrons. So just by looking at the valence electron count themselves, we can see that most likely our A, B, D, and E will fulfill the octets, whereas C doesn't have enough electrons to even make it to 8. So which one will form a Lewis dot structure, a center atom with less than an octet? Well, that's going to be C, because we don't even have 8 valence electrons to put into our Lewis structure. All right. We're going to move on, unless there's questions. Feel free to ask questions. We're going to move on to the next one. I don't even know what number this is. Number 11. Number 11. Which of the following is an isomer of this molecule? I will draw structures for other ones. Just trying to do as many as possible. So which of the following is an isomer of this molecule? Now, isomer just means, so if I were to do this, isomer equals same number of atoms, but different arrangement. So we're going to look for the one that has the same amount of carbons, hydrogens, and oxygens, just different structure, different arrangement. And that's all an isomer is. Same number of atoms, different arrangement. Now, let's count up the atoms here. Well, we have 2 carbons, we have 3 and 6 hydrogens, and we have 1 oxygen. And so this here is the total number of atoms in our molecule here. We have an oxygen, and I noticed a couple answers that don't have oxygen. So because they don't have oxygen, they don't have the same number of atoms, so we can cross those out. Then we have this one here, choice B, has 2 oxygen. Well, we only want a molecule with 1 oxygen. And then that's going to be not the answer. E has 1, 2, 3, 4 carbons. And that 4 carbon means that we have different number of carbons here, so that one's not going to be the answer. And the only answer that has 2 carbons, 6 hydrogens, and 1 oxygen is choice C. It is C. Nice job, everyone. Beautiful. I saw a question in there, resonance. Resonance is slightly different. Resonance, you'll have the same connectivity in terms of a like a nitrogen bound to an oxygen bound to, like this, for instance. This is a proper resonance structure of something, but then we can move those double and triple bonds around. And so it's still going to have the same connectivity, the same arrangement. It's just different double or triple bonds, single bonds, different types of bonds between them. Isomers more have to do with connectivity. So if I were to do CH3 bound to an oxygen bound to a CH3, that's what this one is. Where this one is more of a CH3 bound to a CH2 bound to an OH. So it looks different. Yes. Awesome. All right. So we're going to go to, we're going to do this whole page. Question 12. I'll go back to question 12. Absolutely. We'll do we'll do the question 12 and then that whole page. So question 12. Which of the following Lewis diagrams best represents the bonding in N2O molecule considering formal charges? So remember, formal charge, there is an equation. The equation is, you're going to, so if I were to write the equation here, the formal charge equation, that's going to equal your number of valence electrons minus your number of non-bonding or lone electrons, so non-bonding electrons, minus your number of bonds. And that is formal charge. Now, when we do formal charge, we're looking at each individual atom. So each atom is going to have its own charge. Now, when you add up all of the formal charges, so let's say, for instance, this had a -1, a +1, and a -2. That's not going to be the case, but if you were to add up all of these charges, -1, +1, -2, you would get a -2. And that overall, if you added up all the formal charges, should equal the overall charge on your molecule. Now, in this case, because we're not given a charge on our molecule, hopefully all of them add up to 0. But what we're going to do is we're going to find the formal charge for each one of these atoms and figure them out. And what we want is the molecule that's best going to represent our N2O is the molecule that has the minimal amount of formal charge, meaning we want either zeros or like ones, preferably on each of our atoms, not 2s, 3s, or 4s. We want something that's minimal. So if we go through, I'm gonna do this a couple different ways. I'm going to go through and solve for the formal charge of each type of atom. What do I mean? Well, we have a double bonded nitrogen here. So I'm going to do double bonded nitrogen. And that double bonded nitrogen, the formal charge is going to equal, well, our valence electrons. Nitrogen brings 5 valence electrons. Then you're going to subtract from that the number of unbonded or lone electrons. So that's 1, 2, 3, 4 that we see, minus the number of bonds, and we see 2. So the formal charge here on this one is 5 minus 4 minus 2, which is a minus 1. Now, every time I see a nitrogen with only 2 bonds and like 4 lone electrons, I can go ahead and put a minus 1 on it. And that's actually, I see another one right here, so we can do that because they're all going to have the same formal charge. This equation isn't going to change. Then we go through and we're going to do them for every single one that we see. We see a nitrogen with 4 bonds. So 4 bond nitrogen, I guess I'll put. Formal charge, our valence electron count is 5. We have 0 lone electrons around that. And then we have 4 bonds. So the formal charge for this 4 bonded nitrogen is a positive 1. So anytime I see a nitrogen with 4 bonds, that's 1, 2, 3, 4, I'll put a positive 1. 1, 2, 3, 4, I'll put a positive 1. And it looks like all of those are done. Then we go ahead and we do the next one. We see, I'll do the nitrogens first. So I see a single bond nitrogen. So single bond nitrogen. And we say formal charge of that equals still 5 minus 1, 2, 3, 4, 5, 6 lone electrons minus 1 bond, giving us a formal charge of minus 2. So that's a minus 2. This is a minus 2. And there's one more type of nitrogen, and that's a triple bond nitrogen. And that gives us formal charge equaling, this is a lot of work for this question. Formal charge equaling 5 minus, we have 2 lone electrons minus 3 bonds, giving us a formal charge of 0. So anytime we have 3 bonds on a nitrogen, that's going to be 0. Then we go ahead and we do our oxygens next. Oxygen, we see a double bond oxygen. Formal charge of oxygen. Now our valence count is going to change because oxygen brings 6 valence electrons. We have 1, 2, 3, 4 lone electrons minus 2 bonds, giving us a formal charge of 0 for any double bonded oxygen, which those are the only ones. Then we go through, almost there. We see here, I see a single bond oxygen. Formal charge equals, lost my train of thought. 6 still, valence electron count, minus now we're doing a single bond, so 1, 2, 3, 4, 5, 6, minus 1 bond that we see there, giving us a total of minus 1. And our final one, we have a triple bond oxygen. And that triple bond oxygen, the formal charge equals 6 minus, where's that triple bond? Here we go. There is a missing pair of electrons. My apologies there. So we have 1, 2, we needed to fulfill that octet rule, right? So we had to put that lone pair of electrons there. So we have 6 minus 2 minus 3 for the number of bonds, giving us a formal charge of plus 1. So we go here and we put plus 1. That was a lot of formal charge. But it's good practice to do this. So let's go through. We want ones that best represent the bonding. Now, when we're doing formal charge, we want to minimize the amount of formal charge, meaning we want either zeros on everything, preferably, or ones on everything. So we want to get rid of anything that has a greater value than 1. We see 2 and 2, so we can go ahead. I'm going to change color so we can see. We get rid of C and D, because those have a formal charge on the nitrogens of -2, meaning that's a greater, more formal charge. We want to minimize that formal charge. Now, if we look at A and B, they are both ones, right? We have -1, +1, and 0. 0, +1, and -1. So they're both minimal. And then if we were to add them both up, we see that it equals the overall charge of 0. But this is where we get into the question of which one, either nitrogen or oxygen, likes to have the negative charge, which one likes to be more electronegative, which one likes to hold that minus. Now, this is where we look on a periodic table, and we're going to look at which one, either nitrogen or oxygen, is more electronegative, which one likes to have more charge, more negative charge. And on the periodic table, in that column, in that period, it goes carbon, nitrogen, oxygen, fluorine. And as we go across a period, we become more electronegative. So oxygen likes to have that negative charge. And because oxygen prefers to have that negative charge over nitrogen, we're going to have choice B be the correct answer here, because our oxygen likes to have that formal charge, or prefers to have that formal charge rather, over nitrogen. That was a lot. Whew. All right, we're going to move on. We're going to do 13, 14, and 15. And then we'll do, I don't know what we're going to do after that, but we're going to do 13, 14, 15, which is here. So, in 13, which of the following Lewis electron diagrams, or Lewis dot diagrams, represents the molecule that contains the smallest bond angle? So now we're getting into some bond angle things. We're getting into VSEPR theory. So what we're going to do is we will first figure out our molecular and electron geometries. So let's go through. I'm going to write EG for electron geometry and MG for molecular geometry. And what we're going to do is we're going to figure out our electron geometries first, and then we'll do our molecular geometries. So electron geometries, remember, with an electron geometry, we take our center atom and we count how many things are around it, other atoms and lone pairs. So in the case of A, our carbon has 1, 2, 3, 4 things around it. Now, the 4 things around it, that's going to be tetrahedral. Yes, the smallest bond will usually have more things surrounding that center atom. Typically, that is true, yes. So 4 things around it, if we were to look at the diagram that we had, we see that that is tetrahedral as a shape. Then we go on to B for electron geometry. That nitrogen has 1, 2, 3 atoms and this lone pair. That counts as something. So we see that it has 1, 2, 3, 4 things around it. That is also tetrahedral. For C, our electron geometry, we see a sulfur with 1, 2, 3 atoms, no lone pairs around it. So this would be have an electron geometry with 3 things that is trigonal planar. And then we see again a sulfur with 1, 2, and 2 atoms and a lone pair that's also going to be trigonal planar. Now, looking at these things, we see something that's trigonal planar, something that's tetrahedral. Trigonal planar, actually, we're just going to go through and then we'll talk about something else with this. So molecular geometry, if there are no atoms, no lone pairs around that center atom, the electron geometry is the same as the molecular geometry. So because there's no lone pairs of electrons or unpaired electrons around that carbon, our molecular geometry is still tetrahedral because molecular geometry takes into account just our atoms. But now we see here with our second one, B, we have this lone pair of electrons with 4 things around it. So we have 3 atoms and a lone pair of electrons. One lone pair of electrons on a tetrahedral is characteristic of a trigonal pyramidal shape. Then we go on. We don't see any lone pairs of electrons around that sulfur. So I'm going to just put a little line here so we can see. Our electron and molecular geometries are the same. So we have trigonal planar. And then we see trigonal planar. We have a lone pair. This becomes bent with one lone pair there. Now that we have our molecular geometries, this is where we're going to get into bond angles. So if we were to look at bond angles now, bond angle for tetrahedral, that is 109.5. Bond angle for trigonal planar, I'm going to skip the bipyramid or the pyramidal and bent for a moment. Trigonal planar, that is 120 degrees. So we have 109.5 and 120 degrees right now. For trigonal pyramidal, because we have that lone pair of electrons, we're going to look back at its electron geometry, which was tetrahedral. And tetrahedral is characteristic of something that is 109.5, but that lone pair of electrons lowers the bond angle. It decreases that bond angle. So our actual bond angle here is less than 109.5 degrees. It's more like 104.5 if you had to give it a number, but this will be less than 109.5 because that lone pair shrinks the bond angle. It kind of compresses everything together on that compound. Same thing here. We have a molecular geometry that is different than our electron geometry. So we go back to the electron geometry. Trigonal planar tells us that we have 120 degrees. But now that we have that lone pair of electrons, we are less than 120 degrees. Now, it's not going to be by much. It's going to be, within 4 degrees or something. So now we have these angles to work with. 109.5, less than 109.5, 120, or less than 120. Now, because these two are less than, we have 109.5 that's less than, or 120. They're only going to differ. They're going to decrease by a couple degrees. So then we can just say that the smallest bond angle here is going to be the less than 109.5, which is choice B. I saw a couple people saying that they just drew the Lewis dot structure and not the VSEPR theory, and that gets a lot of people. That definitely gets a lot of people. They'll just look at these and say, well, the smallest bond angle looks like it's, we have this one here or something like that. We're talking now in 3 dimensions, so it's going to look a little different. Whew. Generally, though, the more things that are around your atom, so we had 3 things around this choice C here, and we have 4 things over here. The more things that you have around your atom, the smaller the bond angle. So the smaller the bond angle, so we can go ahead and cross off C and D right away because they only have 3 things versus 4 things. And then that lone pair of electrons shrinks everything. So if you were to do this and not write everything out, you just look at the number of things around your atoms, your center atom. Whew. All right. Hello, everyone. We're almost done. We're going to go over a couple more types, probably like 6 more problems before I have to head off. But all of these problems and the answers are going to be available, and this live is going to be recorded. or is being recorded and will be posted on YouTube as well. So let's go on to number 14. The hybridization of the carbon atoms in the molecule represented above can be described as what? Well, we were talking about hybridization for a little bit ago. Now, hybridization, we're going to look at the amount of things around that carbon. So if I were to just take this carbon and write it down here, we have that carbon, and then we have another carbon attached. I'm only going to look at what's attaching to this one carbon here. Now, when we look at hybridization, we could do the whole orbital thing. We could look at that, but we know our little trick. We count up how many things are around that carbon, how many other atoms and or lone pairs, and we see that we have 1, 2, 3, 4 things. And 4 things leads to a hybridization where we have an s orbital. It'll always be one of the s's, and then we'll add some p's. P, 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 P. So s, we add things until we get to the number of things. So s, we'll always have a maximum of 1 s, 3 p's, 5 d's, whatever it might be. And then we just simplify, right? This becomes sp3. So we have 4 things. We have 1 s, 3 p's, giving us an sp3 hybridized orbital, which is choice C. Let's go on, because this one is similar to the one above. What is the hybridization of the carbon atoms in a molecule of ethine, represented above? So if we look at just at one of those carbons, we have a hydrogen, a carbon, and another carbon. How many things do we have around that carbon? Well, we have 1, 2 things around that center carbon. And then 2 things, we give it 1 s. It will always only ever be 1 s. And then we add our p's. Well, we only need to add 1 p because we have just 2 things. So the hybridization here, we don't even need to simplify because we only have 1 of each. This becomes sp, which is choice A. Nice job. I saw some people get it. Amazing. Now, I also saw a question about sigma and pi bonds. So let's talk about sigma and pi bonds. So sigma and pi bonds go hand in hand with question number 16. 16 asks, which of the following molecules contains exactly 3 sigma bonds and 2 pi bonds? Well, let's first describe what a sigma bond is and a pi bond is. Sigma bonds, so everything's sigma, that's going to be a single bond. Absolutely, you will always, so every single thing that we bond together, hydrogen, chlorine, the bond between those will have a sigma bond. Everything will always have a sigma bond because it's just going to be a single bond. Pi bonds, that's when you get into your double and triple bonds. That's where it gets a little interesting. Yes, you're going to need to figure out the Lewis structures, absolutely. So I'm going to draw just a random molecule here. I'm going to draw, let's do something like this. This, and then we'll have oxygen. No, I want another carbon. We'll do another carbon, then we'll do oxygen bound to a nitrogen bound to 2 hydrogens. We'll do this for now. Something like this. So with this molecule, this doesn't actually exist. Now it does. That's what I meant to do. There we go. So like this giant molecule here, this very giant molecule, we can figure out how many sigma and pi bonds are in here based on the number of single bonds and then the number of double bonds. So every single time we connect 2 atoms together, we are going to form 1 sigma bond. So every bond, every time we connect things together, that's going to be one sigma bond, including the ones for double and triple bonds. So one of those bonds is also going to be a sigma bond. Every single time we connect two things together, those are sigma bonds. So everything in red here is classified as a sigma bond. But then everything else, every time that we have an additional bond for a double or two additional bonds for a triple, those are going to be our pi bonds. So anytime that we have a double bond, we'll have one sigma and two pi bonds. Anytime we have a double bond, we'll have one sigma, one pi. Anytime that we have a triple bond, we'll have one sigma and two pi. So if we were to count up the amount of sigma bonds here, everything in red, 1, 2, 3, 4, 5, 6, 7, 8, this would have, I don't know why I did 7, 8 sigma bonds, and we have one pi bond. 8 sigma, 1 pi, exactly. So that's a very brief overview of sigma and pi. Let's go ahead and figure out this question. What I'm going to do, just for the sake of time, I am going to draw out the Lewis dot structures without sort of talking about how I'm doing it. I'm just going to quickly draw out those Lewis structures. So for A, that's C2H2. That's a triple bond between those two carbons. For B is CO2. And I will also draw in the lone pairs. C, we have HCN. D is SO3, which is SOO, all these lone pairs. And then N2, that is an N triple bound to another nitrogen. So those are the Lewis dot structures. So when we're going through these, remember, we're going to first figure out how many single bonds or how many things we're connecting. And those are going to be our sigma bonds. So we have a connection here, and a connection here, here. So anytime we're connecting two things together, we're going to highlight it in blue, and blue is going to be our sigma bonds. So we can go ahead and add up all of our sigma bonds. We have 3 blues here for 3 sigma. We have 2 sigma bonds, 2 sigma bonds, 3 sigma bonds, and 1 sigma bond. Then we can go ahead, let me choose, I guess I'll do green. Everything left over, so everything in green, those are going to be our pi bonds. So we have our pi bonds, which will kind of cover over. There is another bond here that kind of got covered up. And so everything in green becomes our pi bonds. So this becomes 2 pi. We have 2 pi bond. We have 2 pi bonds, 3 pi bonds. This was 3 sigma and 3 pi. And then we also have 2 pi bonds here. So we're looking for the one with exactly 3 sigma bonds and 2 pi bonds. And the only one here that has 3 sigma and 2 pi is choice A. And that all came from looking at the Lewis dot structures, figuring out how many connections we're making. Each connection is a sigma. So every blue thing, anytime we're connecting something, gets 1 sigma, and then everything else gets pi. So 3 sigma and 2 pi. All right, let's see here. How's everyone doing? Don't worry, all of this is going to be on YouTube. Don't worry. I record the lives, or TikTok does at least, and I'll download it. I'll put it on YouTube after this, and then all of the answers and stuff, as well as the blank PDFs, those are available on my link tree. If you just click the link in my bio, it'll take you to a Google Drive where you can download all of those. My YouTube name, I believe, is the same. It should be the same as my TikTok, except without the period. It also is on. I have all of my accounts linked on the link in my bio. But all of this stuff is available, and if you are having trouble visualizing things in 3 dimensions, then check out PhET. That is also linked on that sort of thing on my bio. PhET Simulation, it goes through, it's a very nice tool to use and visualize things. All right, I know I said 9:15 Eastern was when I was going to stop. I want to go over just a couple more here. Let's do let's talk about number 22. So 22. So 22, which of the following molecules has the shortest bond length? Well, when we're talking about bond length, there's a general trend that we look at. If we were to look at like a triple bond versus a double bond versus a single bond, these go, as we increase the number of bonds between something, our bond length is going to decrease. So this is going to have, a triple bond will have a smaller bond length than our single bond. So this will have a higher or a larger bond length. Now, looking at these molecules, nitrogen, N2, diatomic nitrogen, that is triple bonded. If you were to figure out the Lewis dot structure, you would see that nitrogen is triple bonded to itself with the lone pairs. Oxygen, that would be double bonded. And then all of the halogens, Cl2, Br2, I2, all of those are always single bonds with each other. So we have a single bond, single bond, single bond. So here we have single bond, and single bond. Now we just said that our bond length for single bonds increases or is longer than a bond length that is triple bonded. So our shortest bond length is going to be the molecule with more bonds. So single bonds only have 1 bond, double bond has 2. Nitrogen, that's a triple bond, so it's going to have a shorter bond length. Yay. Oh, thank you. I try my best to make it as understandable as possible. Chemistry is a tough subject. It took me years and years and years to understand hybridization in a nutshell. It took me about 3 years into my undergrad to fully understand hybridization. And I still don't fully understand it, but I can teach it a little bit easier. Someone asked if I ever do Gen Chem 2 topics. Yes. So right now, because the AP test is coming up, I'm doing a lot of review for the AP, but there are a lot of things intermixed with AP. A lot of the videos that I do right now am doing focus on titrations, which is a lot of Gen Chem 2, along with equilibrium and so on and so forth. Intra and inter forces, those I will be going over on my next couple lives. So that's unit 3 of AP Chem. That's intermolecular forces and solutions. So that'll be on Saturday and on Tuesday. And there is a schedule. If you just click the link of lives, there'll be a schedule with all of those. You're more than welcome. We're shooting for a 5. You could also, what I found out, you could also leave half of the exam blank for an AP test and still walk out of there with a 3. So everyone is so worried about trying to get a perfect score, but you really don't need a perfect score to get a 5 on any AP exam, especially chemistry. You could leave half. So the thing is, that other half has to be fully correct. That's the only issue, is it has to be fully correct for that, the other half. But yes, so the general thing is, if you get half the test wrong, you'll still get a 3, which is not bad. And if you're aiming for a 5, you don't need anywhere near perfect. You're going to want to still freshen up on a bunch of stuff, but you don't need perfection. So if you don't know something, move on. Move on. Okay. I want to answer a couple of your questions. So if you have a specific problem or a molecule or anything that you want to know the Lewis dot structure for, how to go about solving those, you only need a 40% correct to get a 3. Yes. So it's something along those lines. You don't need a ton. So if you have a question or a molecule that you want me to kind of go over, by all means, drop it in. Or if you have a question about something, I'll stay on for like another 10 minutes because I like doing these. Increasing polarity. So increasing polarity comes from a difference in electronegativity. So if we go to something like this one here. So difference in polarity, it all has to do with electronegativity. Now you'll more than likely be given these if you're quizzed about it specifically. But then you could also follow the general trend. So if you're not given these actual values from a table, then you would be follow the general trend of electronegativity. But what you would look at is the difference in your bond electronegativity. So nitrogen has an electronegativity of 3.0. Hydrogen has a value of 2.1. So when you do the difference, the overall polarity of that bond, the dipole moment is what we say, is 0.9. And you would do that for all of the bonds that you need to sort of order. You would figure out, okay, well, we have hydrogen is 2.1, fluorine is 4.0. The difference between those gives us our dipole. And you would figure all of those out, and then you can just organize them in terms of least to greatest or greatest to least. A smaller change means that it's less polar. A larger change means that it's more polar. So anything like hydrogen and fluorine, this 1.9, that would be much, much polar than something like carbon and hydrogen. Let's see. In high school, I would guess at this and just be like, oh, I did that for bio. Let's see. How to know which has a stronger lattice energy, like LiCl or NaCl. So that has to come from this, which is Coulomb's law. So Coulomb's law states that the force of attraction, or the internuclear or potential energy force, is proportional to the charges on each of those ions and the radius. So we have the charges of those ions multiplied together divided by the radius of the internuclear distance, or the distance between the two things, squared. Now, I didn't go over this one on the multiple choice, but let's go through it. It's number 5. So the lattice energy of a salt is related to the energy required to separate ions. For which of the following pairs of ions is the energy that is required to separate the ions largest? So we're looking for which one has a large F, right? So we had this not equals, but is proportional to the charges multiplied together over the radius squared. So here, what we're looking at is the charge of the ions and the radius squared. If we're looking for a large F, well, then we want one of two things. We either want high charge, or we want small radius or small atomic size. Because if we multiply something that's larger together, we'll get a larger value. And if we divide by something's on the numerator that's smaller, then we'll get an overall larger value. So we want either one of these things to be true or both of these. So if we look at something like our charges on our ions, we see that Na Cl, sodium, chlorine, cesium, and bromine all have a 1 charge, +1 and -1, whereas magnesium and oxygen, as well as calcium and oxygen, they have a 2 on their charge. So because magnesium and oxygen and calcium, and because C and D have larger charges, and we're looking for a larger F or a larger lattice energy, those are going to have a larger lattice energy than something like A and B, where they only have a charge of 1. So we can go ahead and cross out A and B. The next thing we want to look at is so we looked at charge. Now we want to look at radius. Now, oxygen is the same. So we want to compare the ion of magnesium and the ion of calcium. So if we were to look at the atomic radius, and it looks here that says the distance between the ions is equal to the sum of their ionic radii. So what we want to look at is the size of the atomic radii. Now, the trend on the periodic table is that as we go from the top right to the bottom left, I don't know why it keeps doing that, top right to bottom left, our radius increases. And on the periodic table, magnesium comes above calcium. Magnitude of charge, yes. Not necessarily the quantity, like the positive or negative, but it's the magnitude of charge, exactly. So because magnesium comes above calcium on the periodic table, and the general trend is, well, as we decrease down, or as we go down a column, we're increasing our size. Magnesium is smaller than calcium, and we want something with a small radius. And so magnesium having a smaller radius gives us choice C. The lithium ion is smaller than the sodium ion. Exactly. So you look at the radius and the charge, and those two factors determine the force or the lattice energy. Nice job. All right. We have a couple more minutes. Let's see. What else do we want to do? What else do you want to go over that's related to this unit? Titrations, I saw. Titrations are a little long to go through. I do have examples of titration problems on I don't know if it's pinned, but I do. If you go to the AP/Gen Chem playlist on my TikTok, like on my page, you'll just scroll until you find all the TikTok videos. I go through a bunch of calculations for the titrations. I do share these. So these problems here, if you click on my profile, there's a link. Click the review session materials link. It'll bring you to all of these practice problems. And then if you go to, and then the recordings will be on YouTube as well. NMR for OChem, that is something that I haven't done NMR in a long time personally. I can understand NMRs, but I am not able to currently right now go over NMR. There's a lot of components to NMR. I do know some creators who definitely go over NMR in detail. Melissa Maribel, I think, is one. Lithium Chonk is another. Organic chemistry tutor, obviously. Khan Academy. I think all of those go through NMR. If I have time, I will definitely go over an NMR problem or something as a video, but I don't have any resources right now for a quick reminder of those. Absolutely. Okay. One more question. I think we're going to end it on one more question. I'm going to look for a nice one. Let's see. This currently is AP chemistry, but kind of ties into any sort of general chemistry units. I'm going to look for a nice one. Let's see. We're going to do Actually, you know what? We haven't actually gone through a bunch of drawing Lewis structures, so let's go through some. We're going to go all the way to the end. We're going to do number 2. So we're going to do number 2. 2, 1, and 2 we'll sort of talk about. So number 2, consider the molecules CF4 and SF4. Draw the complete Lewis electron dot structures for each species. So here we're asked to solve or write out the Lewis dot structure. Now we're asked to do 2 of them, so I'm just going to draw a line. That way we have one on one side and one on the other. This is chemical bonding. This is compound structure and properties, unit 2 of AP Chem. So let's go ahead and draw the complete structure. Let's start off with CF4. So CF4, the first thing we want to do is figure out the number of valence electrons. So we look on the periodic table and we see that carbon is in group 4. So that's going to bring 4 valence electrons, and fluorine is in group 7. So that's going to bring 7, but we have 4 of them. So we have to multiply that 7 by 4. So the total number of valence electrons that we have in CF4 is 32. So we're going to go ahead. We are going to figure out our center atom now that we have our total valence electron count. Center atom, we look for the least electronegative atom. So between carbon and fluorine, we know fluorine is the most electronegative, but if you didn't know, you can look on the periodic table, look on the trend. The top right is the most electronegative. The bottom left is the least electronegative. So carbon is going to be our center atom. I'm going to do blue. So carbon is the center atom. We can go ahead, now that we figured out our center atom, we go ahead and plug in or draw in the rest of the outer atoms around our center atom. So we have 4 fluorines to put around our Lewis dot structure. I'm using notability. So then we can go ahead, connect all of our outer atoms to our center atom with a bond. 1, 2, 3, and 4. Now that we've used some of our valence electrons, let's see how many we have to work with. We have how many we have left, actually. So we've used 2, 4, 6, 8. I'm going to just keep going here. Subtracting 8 from 32, we have 24 more valence electrons to put into this system, into this structure. We always start working outer, so working on our outer atoms and working our way in. So each one of these fluorines needs to fulfill the octet. Fluorine wants to fill its octet. So we're going to put another 6 valence electrons around each one of those fluorines. And that'll fulfill the octet. Let me redo those. 1, 2, 3, and 4. Because we have 2, 4, 6 lone electrons and 2 from the shared bond. So now we have, let's see, how many did we put in just there? So all the red ones, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we have used all of our valence electrons. We don't have any more that we can put into our Lewis dot structure. So then last thing to do is check and make sure everything is happy. Each one of the fluorines has 8 valence electrons around it. Those are happy. And our carbon has 2, 4, 6, 8. So that is also happy. So this is our Lewis dot structure. And what do I mean by happy? Well, it's just that our atoms either fulfill the octet, the doublet, or are expanding that octet. Now let's go ahead and do the same thing, but with sulfur. And I already see a couple people saying some stuff about this. So sulfur brings 6 valence electrons. It's in group 6. And we know that fluorine from over here brings 7, but we have 4 of them. So we have a total of 34 valence electrons. Sulfur is less electronegative than fluorine. So we can go ahead, put that in the center, as well as our fluorines around it, and connecting them each with a bond. We have used 8 so far, so we subtract out that 8, giving us 26 valence electrons left. go ahead, we work outer in for the remainder, right? So we're going to put our lone electrons, our lone pairs of electrons, around our fluorines first. And just like before, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 valence electrons. But unlike before, now that we have 2 more valence electrons left. Before, we didn't have any, so we didn't have to worry about this. But we have 2 more valence electrons left. Each one of our fluorines is happy. It does not want any more. It has a full octet. It cannot expand its octet. It's not in the 3rd period. So what are we going to do? Well, we work outer and then we go in. And since we can't put any more valence electrons on the outer, those 2 remaining electrons get put on the center atom. So now we use those 2 more valence electrons, giving us no more left. And sulfur being in the 3rd period, I think, it's after phosphorus, it can expand its octet. So even though we have 2, 4, 6, 8, 10 valence electrons around that sulfur, that is okay because it can expand its octet. So those are the 2 Lewis structures for CF4 and SF4. And then in terms of molecular geometry, account for the fact that the CF molecule is nonpolar, where the SF molecule is polar. So if we were to do molecular geometries, well, first and foremost, we want to do electron geometry. Electron geometry is count up the number of things, including lone pairs and atoms, around that center atom, and that tells us sort of what our geometry is. So our electron geometry for CF4, we have 1, 2, 3, 4 things around it. 4 things tells us we are tetrahedral. Now, because we don't have any lone pairs of electrons around that center atom, our molecular geometry is the same. So our electron and molecular geometries are the same here. Whereas for SF4, our electron geometry is 1, 2, 3, 4 atoms and 1 lone pair of electrons, gives us 5 things around our atom, our center atom, and that tells us that we are trigonal bipyramidal. Bipyramidal. But then our molecular geometry, because we have that lone pair of electron, it changes. And that lone pair of electrons on something that's trigonal bipyramidal gives us a molecular geometry of seesaw or sawhorse, whichever one you learn. They're the same thing. So in terms of molecular geometry, account for the fact that CF4 is nonpolar, whereas SF4 molecule is polar. Well, CF4 has a molecular geometry that is tetrahedral. SF4 has a molecular geometry that is seesaw or sawhorse. That lone pair of electrons alters the molecular geometry, because if it wasn't there, that lone pair of electrons, they would be the same. But because it's different, it creates a polar molecule because now we have an unequal distribution of electrons around that center atom. So because we added in that lone pair, now we have a polar molecule. And that's the general sense of this question. Whew, that was a lot. I hope this was very helpful. I'm going to turn this around. Let's see if I can do it quickly without disturbing anything. My name's Bradley. I am going live for AP Chem for the AP test, but any sort of chemistry that you need help with. Oh my goodness, I'm so glad that you get it. Absolutely, it is my pleasure. I don't think it's a pinned video anymore, but the next time I am going live is Saturday at 5 p.m. Eastern. And we are going to be going over Unit 3, Part 1 of Unit 3. So we'll do intermolecular forces and solutions, but because Unit 3 is such a very big topic, big unit, we're splitting that up. So next Saturday, there will be a Unit 3 Intermolecular Forces Solutions Chemistry at 5 p.m. Eastern, and then Tuesday at 7. So next Tuesday, I think it's the 13th and the 16th are the IMFs. Is there a continuation on this? And thank you. Of course, first of all, there's currently not a continuation of this unit. I will be posting practice problems and things for you to do and me going over things, but in terms of a live session, I don't have one scheduled. If I end up having more time, I will definitely kind of go over more of these, but I don't know if I have time right now. I don't have posted notes specifically. I do have everything that we go over is posted on YouTube, and then the packets, so all of these question packets that I make are available for you to try. All of the notes that I have are currently not my notes that I use, that I pull information from, so I'm not at liberty to share someone else's notes. So until I make my own, I unfortunately cannot share those. But I hope you all have gained something from this, whether it be just a voice to listen to as you fall asleep, or if you learn something chemistry. Remember, as the AP exam comes up, or any finals or tests, no matter what, chemistry is difficult. It's okay not to know things. I mean, I failed a couple of my chemistry courses, and look where I am now. So you're not going to know everything, and that's totally okay. Just do your best. Keep on being amazing. You got this. I know you do. All right, have a great night, everyone. I will see you all in a couple days. Bye.